Okay, so welcome back, everyone. Let me just quickly share my screen again to remind everyone of this morning's program. So following the presentations by Professor Bish on the general organization and concepts of the new generation of the Eurocodes, and the presentation by Professor Labbé on the seismic action formulation and definition, we will now move to the presentation by Professor Dolšek from the Faculty of Civil and Geotechnic Engineering in Ljubljana. He will be telling us more about the modeling, analysis, and verification rules. So Professor Dolšek is a professor of civil and environmental engineering in Ljubljana. He is very well known for his research in the fields of performance-based seismic design of structures, mostly using probabilistic methods, also with the consideration of the seismic performance of the built environment. He's been involved in many European projects, a significant number, as you can see, as he is also currently working in the European projects bodies and METIS. He's a member of the Slovenian Chamber of Engineers, Institute for Standardization Technical Committees. And he's also been directly involved, as all the other participants and presenters, in the working groups of this new generation, specifically 1 and 13. So, Professor Dolšek, thank you very much, and I will leave the floor to you.
Thank you, Ricardo, for the introduction, and thank you for the invitation to give this webinar. So maybe before I start, just a small note that first I was asked to make a presentation mainly on the nonlinear static analysis in Eurocode, but later on, maybe 1 week ago, so I was asked to give a more general presentation or webinar on modeling, analysis, and verification rules. And because some of these parts were already presented by Professor Bish and Labbé, maybe there will be some repetition because of them. Okay, so the content of my presentation, it's mainly related to the Eurocode 8.1.1. It's section 6. It's a general section on modeling, analysis, and verification. And this section has the following subsections. And firstly, I'll talk about the general part of this section and then about the modeling. I'll skip the discussion on the seismic action for analysis, which was already presented by Professor Labbé. Then I'll talk about the force-based approach and nonlinear static analysis for displacement-based approach. Maybe here a short notice. The title of 6.4, it's force-based approach, while the title in 6.5 in the current draft, it's nonlinear static analysis. Perhaps this should be a little bit more harmonized in a way as it is perhaps written here. Then I will also skip the discussion on response history analysis, and I will then discuss about the verification to limit states. So if we go to the 6.1, to the general, so in this subsection, Eurocode introduces, let's say, the can be done, and it basically defines the two approaches for earthquake-resistant design. These are the force-based approach and the displacement-based approach. And the third alternative, it's response history analysis. So use of nonlinear response history analysis for earthquake-resistant design. And it was also partially described, at least how the seismic action is selected for this part. We all know that force-based approach is based on linear elastic analysis, and the code prescribes two types of linear elastic analysis, a lateral force method and response spectrum method. Because it is a linear elastic analysis, we are aware that it approximately should be accounted for the overstrength, and the nonlinear response through a concept of reduction of seismic forces, which is in Eurocode introduced by the behavior factor. Of course, this is, let's say, the consequence of the scope or of the code, where the major or the first goal of the code is that we protect human lives and we allow, let's say, damage in the buildings, while in the case of linear plastic analysis, we cannot simulate the damage. And from this point of view, we have to somehow account approximately to the nonlinear behavior, and this is done through the behavior factor, which means that we reduce the seismic action. This is basically the same concept as it was already used or practiced through the Europe based on the current code. The force-based approach can be used to verify the significant damage limit state. This is, let's say, in relation to the protection of the human lives. This is partially also historically. I will not discuss this into details because as was presented before, the return period of the ground motion parameters which are used for the verification of significant damage limit state are related to the return period for 175 years, and this is 10% probability in 50 years, which means that there still need to be, let's say, some safety margin to the collapse of the building. Otherwise, we will not be safe against the ultimate or the final or the main goal of the code, which says that we should protect the human lives. Of course, the force-based approach can be used also for the verification of the damage limitation on operational limit state based on the Q equal to 1. And code also prescribes that design displacement obtained from the seismic analysis can be used, but they have to be multiplied by the behavior factor for displacements, because we are using the reduced seismic action. Then in the general part, code also introduced the displacement-based approach, which is usually termed, let's say, in the or another term which is used is performance-based approach, but in order to have some analogy with the force-based, so it's termed as displacement-based approach. It's implemented through a nonlinear static analysis, so it is not meant that it can be used based on the response history analysis. The good things, or let's say the advantage in comparison to the force-based approach, that explicitly accounts for the structural nonlinear behavior. And there is also, let's say, one novelty that of course, first, the design displacements are directly obtained from the analysis based on the R-mu-T relationship, which is the concept already practiced in the current code. But the novelty is that nonlinear response history analysis of the SDF model can be used to calculate the target displacement. This is Annex C, which I'll also talk a little bit about that. The verification rules, the concept is the same as in the current code, but there are also some, let's say, new concepts. First concept is that action effect should not exceed the resistance. This is the same as in the current code. And for the force-based approach, so the generalized forces are represented by the action effects at the member level. So for each member, we have to verify that action effect is not exceeded the resistance. Basically, we also, let's say, design the resistance if we are using force-based approach. In the displacement-based approach, so there are two, let's say, levels of the verification. One is based on the generalized deformation. These are used for ductile plastic mechanism, or based on general forces for the brittle mechanism, as already explained in the first presentation by Professor Bush. So if we go now to the section 6.2, it's about the modeling. So the description of the modeling in this part of the code, it's very general. So the rules are mainly descriptive, and also because it is expected that the engineer has adequate knowledge on modeling, which is quite challenging in the case of the nonlinear analysis, but also there are a lot of additional rules for modeling in other parts of the Eurocode 8. So here are only the general concepts introduced. So the general criteria or description of the modeling is that the model of the structure should be adequate. So this means that the stiffness, mass, damping, strength, and deformation capacity should be adequately described by the structural model. And the details, of course, are provided in the relevant parts of Eurocode 8. The member properties should be based on the mean values of the property of the material. For example, if you are using force-based approach, that means that mean elastic modulus of the material you should select. Also, the ancillary elements which may influence the seismic response should be accounted in the model for seismic analysis. For example, if the mass of these elements is high and so on. And also the influence of adjacent structures should be considered so that we don't have any collision of the two buildings. Then this part of the code is decomposed into two additional subsections, which provides additional rules for linear elastic analysis and additional rules for nonlinear analysis. So in the case of linear analysis, so it is prescribed that elastic stiffness should be equal to the second stiffness that corresponds to the elastic limits of the structural members, and that the source structure interaction should be taken into account in the case of the adverse effect. So the first bullet is basically the same as in the current code. Also in the part 1.2, it is also, let's say, described that if there is no precise analysis, the second stiffness can be based on the reduced moment of inertia for 50%. Additional rules for nonlinear analysis. So the minimum is, or let's say, first we have to extend the model for the linear analysis to the nonlinear analysis, and the minimum is that the bilinear force deformation relationship at the member level is taken into account. Trilinear force deformation relationship may be used for reinforced concrete structure and reinforced masonry structures. And this third bullet, it's maybe important because there are rules for defining deformation capacity in the code, and it's prescribed in this already here in this general part that cyclic degradation should be considered, because we are using the, let's say, pushover analysis, so we are not simulating the effects of cyclic degradation, and this should be considered in the definition of deformation capacity. When we are calculating the resistance for bending, we should also consider the effect of axial and shear forces for the force deformation relationships. And of course, if someone is using the response history analysis, hysteretic behavior should be taken into account. Okay, so this was, let's say, a brief introduction of this general part of section 6 and the modeling. And now I'll go to the 6.4, which is about the seismic analysis for force-based approach. So as already said by Professor Labbé, the seismic action is based on the reduced spectrum, which is currently in terms of the design spectrum. Also in the draft of the new Eurocode, when the reduced spectrum is defined at the beginning, it's still the terminology reduced design spectrum. So this perhaps should be somehow addressed in the next, let's say, modification of the draft. And yes, the ductility classes are still present as discussed by Professor Bish. So there are 3 ductility classes, DC1, DC2, and DC3. There is a difference in comparison to the current code. This, let's say, to very roughly describe the difference. So DC1, it's very similar to the ductility class low. DC3, it's very similar to the ductility class medium, while the DC2, it's something in between. So it accounts for the ductility partially, but only on the local level of the members. As well, that the global plastic mechanism is controlled, but not designed. So this is the, let's say, the novelty of the code. And of course, in the relevant parts of the Eurocode, there are definition of the behavior factor for these 3 ductility classes. And the novelty with the behavior factor is that that it is now decomposed into the 3 components. So it's the overstrength factor. It's composed in the QR and QS. QR accounts for the overstrength due to the distribution of the seismic action effects in redundant structure, as explained by Professor Bish. This is basically the relationship between the alpha U and alpha 1. Then there is another component of the overstrength factor due to all other sources, and this is equal to 1.5 if it's not prescribed different in relevant parts in the code. And then there is a deformation capacity and energy dissipation capacity component of the behavior factor QD, and this is greater than 1 for DC2 or DC3 ductility class. Maybe a small warning to the presentation of the Professor Bish. You may recall that it was nicely presented how these 3 components of the behavior factor can be, let's say, discussed or presented in the terms of pushover curve. But please be aware that behavior factor is related to the significant damage limit state and not to the ultimate displacement as presented at the diagram of Professor Bish. Of course, this is because we are verifying, say, the structural performance for the term period of 475 years in the case of buildings of ordinary importance of consequence class 2. And there is also a rule given that we should use 1 ductility class per building, but the component QD of the behavior factor can be, of course, different in horizontal direction. This is mainly in the case, let's say, of steel buildings, so you can have different structural systems in one and the other direction. Okay, also Professor Labbé introduced the reduced spectrum. I will go very briefly through this part. The concept is the same as in the current code. The formulas are different. So for the horizontal component, the reduced spectrum, it's elastic spectrum divided by the reduction factor. And we still have a limit that the spectral acceleration should not be less than this value. So beta times the S alpha corresponding to 475 years, which is basically the same as in the current code. The difference is that the ground motion parameter is not anymore the PGA. The reduction factor, it's the period, this QR, it's period dependent, as already discussed and nicely presented by figure by Professor Labbé. So basically very similar as currently introduced in the code. And for the vertical component, we can consider the behavior factor equal to 1.5, and greater values should be justified based on the analysis. Okay, if we go now to the type of the analysis which can be used for the linear based force-based approach, there are 2 analyses. So the lateral force method basically the same as in the current code. There are some, let's say, improvements. So we don't have anymore the simplified coefficient-based formulas for defining the period of the structure, but it is introduced the Rayleigh formula for the period of the fundamental mode. It's not completely, let's say, the Rayleigh formula because it's considered only the let's say, the force at the top of the structure in a single, in a one direction and in one level. But basically provides the same results. So this is, let's say, a novelty and an improvement in comparison to the current code. Then regarding the response spectrum method, also again it's the same. The residual mode is introduced. This is the new. You know that in the response spectrum method, the question arises how many modes you should take into account. And the rules of associated with the sum of the model effective masses, it's still there, but there is also, let's say, a set residual mode is introduced, and this is related how many, let's say, modes can be used, and if you use, let's say, the modes, I think up to TD, then you can consider the residual effective model mass to the residual mode. So there is no any more rule that you should consider all the modes to which 5% of the model masses corresponds to. The new thing in this part, it's also that the combination of model responses is explicitly defined by the formulas. This was not done in the current code for the C2C combination rule. And it's also, let's say, explained when the SRSS combination rule should be used and when the C2C. So this is new, but this part, I think it's not so, let's say, important because nowadays the software support, you can always probably use C2C, which is more precise in the case of the combination of model responses. Then for the displacement, it is described that displacement can be based on the analysis, but multiplied by the behavior factor for the displacement, which is similar as in the current code, and also the combination of the effects of the components of the seismic action are still the same as in the current code. So we can use as a SRSS rule or so-called 130 rule, which means that we consider 100% of action in one direction, 30 in the other direction, and 30, let's say, in the third direction if we use also the vertical component of the seismic action. Okay, so this is about the 6.4 force-based approach, and then if we go to the 6.5 nonlinear static analysis. Here I will present a few slides about the theoretical background from this analysis, and then I'll talk about the Eurocode 8, which is the section 6.5, which is decomposing the following parts of general lateral loads, capacity diagram, equivalent single degree of freedom model, target displacement. This is Annex C, which is also, let's say, one option to calculate the target displacement using nonlinear response history analysis of the single degree of freedom model. So the theoretical background for the pushover analysis, or let's say rationale for the pushover analysis, is explained in this slide. So if you would like to calculate the seismic response of the building, so we have to, let's say, set up the equation of motion at the level of structure. This means that we have a system of n dependent non-homogeneous second order differential equations with the nonlinear coefficients. So we have the inertial forces, damping forces, internal forces, and then the external load. the good thing of such description of the problem is that we simultaneously addressing the interaction between the seismic demand and seismic capacity. So the seismic capacity is hidden here in this model, while the seismic demand, then it's, let's say, an act of the forces between the inertia, let's say, damping, and of course the external load. And usually this is too complex for practical application, at least for the buildings, let's say, which are of ordinary importance, when the investment is relatively low for the design of such buildings. Then the solution, or the simplification, which can be shown from the theoretical point of view, is that, or the idea is that we simplify this n-dimensional problem to a single degree of freedom. So there, of course, for this are needed the assumptions. So the first assumption is that the shape of displacement vector is independent of time, and also, which means not only on time, but also on the damage of the structure. And then we should consider the ground motion only in one direction. Why? Because we would like to get the single degree of freedom model. So if we have a single degree of freedom model, we cannot have, let's say, the ground motions actions in different, or in more than one direction. So the consequence of this assumption is that we can simplify the n-dimensional equation of motion to the equation of motion for the single degree of freedom model. And we get the non-homogeneous second order differential equation with the nonlinear coefficient. So the nonlinear coefficient, basically this part, usually it can be also that one, while the mass it's usually considered constant. And how this equation can be solved? Often it's solved indirectly by so-called R-mu-T relationship. This is, let's say, the classic N2 method introduced by Professor Pfeiffer. And can be solved, of course, also directly by numerical integration. How this is done, or how the transformation from the multi-degree to the single degree of freedom model is presented in one of basically this is the encyclopedia of earthquake engineering. But the good thing is in the new code that both options are foreseen in Eurocode. So engineer can select either to use the simplified R-mu-T relationship, or can let's say, use and solve this equation numerically. So just to summarize this theoretical background, so in general case, we have equation of motion in matrix form, so n-dimensional. The good thing is that this equation simultaneously, let's say, account for interaction between the demand and capacity. But in the pushover-based method, we decompose the capacity and demand in two parts. So the capacity is still based on the multi-degree of freedom model, but we neglect the inertial forces and damping forces. So we use the static system. So we have to assume some lateral forces. We perform pushover analysis and we get the capacity diagram, which is termed now the pushover curve in the code, which is the relationship between the, let's say, base shear and the top displacement. While the demand is then calculated either by simplified R-mu-T relationship, which means that you don't need to calculate any, let's say, dynamic analysis, but you use simple formulas. For example, in the Eurocode, the top displacement depends on the spectral acceleration, field acceleration, elastic displacement, and the period of the single degree of freedom system. And then you have a simple formulas to calculate the T star. And note that about the terminology, which I show here, the displacements are marked by U, but in the code, the displacements are marked by D. Then the other option is the nonlinear dynamic analysis of the single degree of freedom model. And in this demand part, we have, let's say, we have to set up the equivalent single degree of freedom model, and we calculate the target displacement. So These are the two approaches. And then when we get the target displacement, we go back, let's say, to the results of pushover analysis and check, let's say, the damage and so on. Okay, so how this is done in the code? So basically, this subsection follows this decomposition. So first we have to define the lateral loads. We get the capacity diagram. We have to set up the equivalent model and calculate the target displacement. And this is also, let's say, the structure of the code. So if you go to the general part, so the code says where and when or for what purpose we can use the nonlinear static analysis. So to verify the structural performance of newly designed structures. This is new in comparison to the current version. To assess the structural performance of existing or retrofitted structures specified in Eurocode 8.3 for buildings, and which is new now also for bridges. And also to verify the structural performance of newly designed bridges, which is also new. And we have to account also the source structure interaction as specified in Eurocode 8.5. It is not prescribed that nonlinear static analysis is used for let's say, for tanks, or for example, in Eurocode 8.4. Though this note is probably correct, but still with the, let's say, the nonlinear static analysis, you can more precisely account for the local nonlinear behavior. And perhaps, let's say, in the future, not in this generation, the nonlinear analysis can be implemented also in structures like tanks. And also there is a note about the multi-mode methods for the pushover based analysis. I'm not going to do that. Okay, then in general part, it's also some description how the assumptions are treated. So because the pushover based method, it's a simplified method, and it says code that seismic action affecting the structure and structural members should be for defined structure, not for all of them, corrected by factors which take into account the effect of higher modes, torsion, and minimum eccentricity. These are the so-called correction factors CP and CE, which are not introduced in the Eurocode 8.1.1, but in the other relevant parts. And with this correction factor, we correct for the demand. There is also a correction factor, I'll talk later on a little bit about that, which accounts for the combination of the horizontal components of the seismic action. This is partially accounted in with definition of this factor, but not for the target displacement. For the target displacement, there is another factor which accounts for this part. And again, it is repeated that, especially for existing structure, the model for the deformation capacity should account for cyclic degradation. So this is important because we use the pushover analysis, so we are not simulating any cycling. We have to account this in the model for deformation capacity. Okay, someone is making some notes here. So in the next part of the nonlinear static analysis, there are, let's say, definition how the pushover analysis should be carried out. So first we have to do assume the lateral forces for pushover analysis, and those are defined for each horizontal direction independently. At least a model pattern of lateral forces should be applied. And there is also the definition how to calculate the total shear force, of course, the sum of the lateral forces. But with this definition that this is alpha times the sum of these forces, it's actually prescribed that the lateral force, the shape of the lateral forces should be constant, which means that there is not prescription of any adaptive methods to be used. Then it's also defined the control displacement. Of course, when you do the pushover analysis, so you have to push it, let's say, beyond the significant damage limit state. But at the location, and you have to control the displacement at the given point of the building. For the buildings, this is usually the center of mass, but it can be defined also in different points. Then when you perform the pushover analysis, you can get the relationship between the base shear and the control displacement. And as I explained before, so the pushover analysis should continue to the ultimate displacement, which is defined, let's say, which is attained at the first member. It can be either ductile, with a ductile mechanism, or to the brittle failure or instability of the structure. Okay, so this is about the procedure of the pushover analysis. Let me try if I can erase this part, so I cannot erase these lines. Okay. Further on, it's the topic about how the engineer can set up a single degree of freedom model. So in this part of the code, in the 6.5, so we are not solving this kind of the equation, but we have to, let's say, define only the equivalent mass according to this formula, which is a classical N2 method. And then we also do not need to define anything about the damping, and we don't need to define the ground motion, because the seismic action it's defined based on the elastic response spectrum. But in order to calculate, let's say, the target displacement, we have to define the yield point of the single degree of freedom system. So this can be based on the bilinear idealization, but first we have to, let's say, transform the pushover curve of the structure to the force displacement relationship of the single degree of freedom model through the transformation factor gamma. There is, let's say, a little bit more general approach, because it is not prescribed in the new Eurocode that mode shape should be normalized to 1, but it's not necessary to be normalized. For this reason, so there is a component from the mode shape. So the target displacement, calculation of target displacement, it's basically the same as in the current code. So if the period of the single degree of freedom system is greater than the TC, then the so-called equal displacement rule is used. So it is assumed that the displacement of nonlinear system is equal to the linear system. But if the period of the equivalent single degree of freedom system is lower than the TC, then in this case, this formula is used, which is basically the same as the R-METU relationship introduced by Pfeiffer. Maybe a small warning. So this is the figure which is taken from that part of the code. And this line actually represents the so-called N2 curve. It's an alternative or proxy for the IDA curve. But if it is based on this formula, it should be a linear function, not curve. Then there is a new parameter which you need to multiply this dt with cdt in order to account for the, let's say, effect to this displacement, to this target displacement from the seismic action on the other direction. So this is done by the SRSS rule, where this gamma dot is based on the participation factor for the same direction as this dt, but due to the loading in the other direction. Okay, if we go now to the target displacement, how it is introduced in Annex E. So basically, the idea of Annex E is to define everything to solve this equation, which means that it's a generalized single degree of freedom model, and which means that it's not necessary that it's bilinear force displacement relationship, this part, but it can be multilinear. And the target displacement, this U, it's done based on solving this equation. And another novelty is that it's not only for the target displacement, but also for limit state spectral acceleration, which is related to Annex F, which is the, let's say, simplified reliability-based verification format. Okay, so how this Annex E structures? So first, it says, yes, you can do the multilinear force displacement relationship. There are different, let's say, examples how you can do that. So you can account not only for bilinear radialization, you can have a softening, or for example, if you have a infield frame, so you can have a collapse of infields, and then you have still the frame carry some loads and so on. So there are the rules how to do this type of idealization. Given in this annex, then the damping coefficient is defined. So this part is defined, but I think here is still a missing part, that the damping model, it's not defined. So it's not the same if you use the damping model, then proportional to the mass or to the stiffness and so on. Because in the software, you have to define also the damping model. It's not enough to define also the damping constant. And then it's also prescribed that high static behavior should reflect the response of the entire structure, not only the one element, because this formula is to simulate the response of the entire structure. Then, of course, the complexity is definition of the ground motion, so it cannot be used anymore by the acceleration response spectrum, but we have to select ground motions. It is prescribed that ground motion should be selected according to Annex D, briefly introduced by Professor Lebet. It is also prescribed that not less than 15 ground motions should be used. Not 7, but not less than 15. And the target displacement is then the mean of the log values of maximum displacement obtained for each ground motion. Okay, now if I go to quickly to the verification to limit states, the rule for the verification is the same. So action effects should be less than or equal to the resistance. But how this is checked depends on the type of method, either force-based or pushover-based approach. The force-based approach may be used for the verification of the significant damage, limit state damage limitation, operational limit state, and of course, overall stability should be checked over turning and sliding. Either you are using the force-based or displacement-based approach. Then for the displacement-based approach, I will not go into details because it was already explained by Professor Bish. So there are basically two ways how to do it. So one is that the resistance is checked based on ultimate deformation at the member level. And in this case, it is distinguished between the ductile mechanism, so this part, and the brittle mechanism. And this gamma RD accounts for the, let's say, uncertainty in the resistance model, while alpha SD, let's let's say, accounts the level of damage of the member. In general, alpha SD and gamma RD can be also, let's say, calibrated to the target reliability, let's say in conjunction in Annex F, but this is not a mandatory part. Alternatively, the resistance can be checked based on the displacement of equivalent single degree of freedom model, but only for those type of structure for which the section 7 does not prescribe the ultimate deformation at the member level, which means that, for example, for masonry buildings and so on. And of course, foundation and soil should be checked in order not to have substantial and permanent deformations. Briefly about the Annex F, because this is, let's say, an alternative for the verification to limit state. It is informative annex. It's introduced a simplified reliability-based verification format. So in this case, the engineer can check the probability, or he has to assess the probability, annual probability of exceedance of limit state, and he has to prove that it's less than the target annual probability. There are different procedures how to calculate the annual probability of exceedance of limit state, but not much about the target probabilities. There is only note it's given that the target probability for the near collapse limit state and consequent class 2, it's 2 times 10 on minus 4. To conclude, for the modeling part, there is not much changing in this Eurocode 811 in respect to the current version, but there are, let's say, novelties in the other relevant parts of the code about the modeling too. For the analysis, the force-based design approach is very similar in the current code. Ductility classes and behavior factors are redefined. For the displacement-based or performance-based design or approach, the novelty is that the correction factor for pushover-based methods are introduced. So there are correction factors for elevation, plane, and the components of horizontal actions. And there is, let's say, more general way how someone can calculate the target displacement through the nonlinear response history analysis. About the verification rules, yes, there are new rules for the displacement-based approach. And the new, it's also the informative reliability-based verification format, which currently does not seem that it's very, let's say, important part, but in future, I think this will become an important part because this annex is not opening, let's say, only the new way how someone can verify the performance, but it links maybe some other processes which are necessary at the national level with the Eurocode. For example, each member state of the European Union has to make some, let's say, vulnerability assessment due to different natural hazards and then send them or report this to the European Commission. Those studies usually are based on reliability analysis, while the design it's not. So this in future can be linked, and also, let's say, the returning periods for the design seismic action can be based on this procedure, dependent on the consequences of the area where the building is located. Currently, this is not done. So I think this is, let's say, a good novelty, which is only informative, but opens the door for the future developments. So with this, I'll conclude my presentation. Thank you.
Thank you. Thank you very much, Professor Dolšek, for both the theoretical overview and for the introduction to the novelties in this new generation. So during the presentation, there were a couple of, there was a comment and a question. So first, there was a comment by Professor Rainer Flesch. I think it should be clearly stated that when modeling consequence class 3 structure using a behavior factor of 1, the stiffness of non-structural elements must be considered in order to obtain a realistic model. I don't know if you want to comment or add something on this.
You read because I didn't saw the comment, so.
Sorry?
So, okay. My comment to this would be like that. So I would not design the buildings for CC3 for Q equal to 1. So this is something which is not very smart to do. Perhaps in a very, very low seismicity area, but otherwise designing very important buildings without taking into account for the ductility, it's not very smart.
Okay, then we had a more practical question by Roberta Apostolska from ISIS in Skopje. So is there any info about difference between the base shear force calculated according to the current version and that of the second version? This could be interesting for design engineers in their daily practice using the new version of the...
If I remember correctly, but Roberta may correct me, this part 43322, it's related to the lateral force method. Mm-hmm. And as I said in my presentation, the lateral force method in the new draft is basically the same. So nothing changes. The novelty, it's let's say the good thing of the new draft is that there is a formula how to calculate the period based on, let's say, Rayleigh formula, which has a very good theoretical background.
Okay. Then Rodrigo Falcão Moreira from Porto in Portugal asks if an alternative to the conventional force-based pushover analysis, such as the displacement-based adaptive pushover analysis, can be used. So target, avoid having to define a lateral load pattern considering the evolution of the lateral load pattern during the analysis.
I didn't catch this question. So this was the question of
Falcão Moreira. So he's asking if there's anything in the code that foresees the replacement of a conventional pushover analysis with an adaptive displacement-based pushover analysis.
I think, as I said, there is a clause which says how you calculate the base shear force, and that is prescribed that you can use, let's say, you can sum the lateral forces which you assume, and then multiply it by alpha factor, which means that the shape of the forces it's prescribed constant. At least in this part 811. Perhaps there are some, let's say, in other parts they did some other definitions, but this is how it is currently.
Okay, I'm going maybe to target the shorter questions first. So then we have another one by Jorge Proença. So for the detailed thank you for the detailed presentation. My question relates to the definition of secondary seismic members. Are there any modifications with respect to the first generation?
I think there are some differences, but currently I cannot answer this in detail. Maybe someone from the group who made other presentation can help, but I can answer this later.
Okay. Didier from ComSecure. So are there more indications on how to take into account the fact that the results of the SRSS or the CQC combinations of spectral analysis are not signed? Should all the combinations of solicitation parameters be taken into account? Should the solicitation parameters be signed somehow? Thank you very much.
There is no difference with the current code, so all the combinations should be taken into account. Yes.
Okay.
This is the problem of the response spectrum analysis. So the difference is, yes, there is no need to use the response spectrum analysis, so you can use the displacement-based approach, for example.
Okay, we can perhaps go back to the question of Professor Georgopoulos. So it's a bit longer. With regard to the practical application of the simplified combination of horizontal seismic actions. So for a column, there are two load cases. So action in X plus 30% in Y and vice versa. that gives 2 times 8 times 8, 32 combinations plus 1 for gravity actions. That makes the total number of combinations of 33. So for the top and bottom of the column, they become actually 66. For 5% of accidental eccentricity, it can then become 4 times this. So in the end, the question is, how is this simplified? So it's a little bit of a, of a comment. And I'm assuming in the end that there have been no changes as well in this part.
There is no changes, but I think there is no need to have so many, let's say, combinations. So if you use the response spectrum analysis, there are much less combinations than in case the lateral force method, because lateral force method you have to take into account also the sign of the seismic action, which in the response spectrum analysis is automatically taken into account. So that would be the, let's say, the answer. The other answer is, again, displacement-based approach will not require so many combinations.
Okay, and we have also one more question by Maria Teresa from Polytechnic of Madrid. So how can the Q displacement be obtained? So the coefficient to obtain the displacements from the seismic analysis, does it match the coefficient of the behavior coefficient? Well, the question is not so clear to me. I'm not sure if it is to you.
It is in the Eurocode 8. It's clearly defined behavior factor for the displacement. It's very similar to the behavior factor for the force-based design, but not completely similar, because you have to take into account that the inelastic response for the buildings, which has a period lower than TC, it's greater than elastic response. So there is a small difference there. Okay. While for the buildings with the period greater than TC, it's a behavior factor for displacement equal to the behavior factor for forces.
Very well. So I think I will thank you very much once again for this presentation, for your time. Thank you all the participants also for the numerous questions. And we will move now to the last presentation of today. I will leave again to my colleague Luca to chair the next presenter.